So reactive power and RMS fundamentals. We're going to start really basic. I promise it'll pick up, but for people here who might not understand power at the conceptual level as well, we're gonna start simple. So power equals instantaneous voltage times instantaneous current, and we're going to be speaking today specifically about AC power. So everything's going to be sinusoidal or pseudo-sinusoidal. So we have a voltage and a current in red and blue here that are perfectly in phase, the peaks and zeros align. And if we multiply voltage times current, we get a positive power, because positive times positive, that does not cross the zero line, which is my dotted zero line. However, this power has a cyclical nature to it. So it has a phase angle of 0, the power factor of 1, and we see this oscillatory power. Now, for a variety of reasons, this is hard to describe. It's got peaks, it's got frequency, it's got amplitudes, and also this is single phase, so it's a little more simple, but we'll stay simple. It applies to 3-phase as well. But this is all positive. But what happens when voltage and current become out of phase in an inductive or capacitive circuit? Inductive circuit being an electric motor, which is what I hope many of you are evaluating. Well, here's an example where we just added a 30-degree phase angle. Our power factor, which is the cosine of the angle, is 0.865. And these are all screenshots from our software. This is not meant to be a sales pitch, but it's just what I used. So we have a phase offset. Our peaks are now 30 degrees misaligned. Our zeros are now 30 degrees misaligned. And 30 degrees at 60 hertz is 1.4 milliseconds in time. So the phase delay is really a delay in time between when voltage and current arrive. So measure this with an angle. You could also measure it with time. It's just angle is frequency independent. But what we see in our power, when we multiply that V times I, again, we're sticking with real simple math, V times I. Our power, my black trace, now has this little negative segment. So we have some positive power and then some negative power. And this is oscillating power. So it does work and then it does negative work, which we can't count that difference of the negative and the positive towards the active power. And many of you may have heard of reactive power or might be quite familiar with it. We'll talk about reactive power a little bit more. But this is the reactive power, is this negative oscillation. So now this becomes even more difficult to describe. We have this real power with a frequency and amplitude and this negative power. And what we get to is we end up averaging power. So that's where we go with this. But I think for the fundamental understanding, we start here. Okay, now purely reactive power, and this is really why I like to show this, is to highlight what reactive power is. So now my voltage and current are 90 degrees out of phase, so our phase angle is 90. Power factor is 0, which our little calculation tool gives negative 200 micro degrees, or it's 0. And we get this perfectly oscillatory power, again, V times I, but because they're perfectly offset, now peaks and zeros are aligned. We get positive power, then we get negative power. These cancel out to create 0 active power on the average. So when we average power over time, we get 0 power output. So this really is, it's in a power line. It is there, but it's oscillating. It's not doing anything useful except creating heat and losses and all this stuff we don't necessarily want. So it's power that's showing up at the wrong time. It doesn't do real work because it's sitting there oscillating. And it limits how much power can be transmitted because it's taking up space in the power line. So it's really not as simple as real power. Real power creates torque, it creates heat, it creates light. It's phase-based. There's also a harmonic element. So this is purely phase-based power factor. We're going to talk about distortion power, which you can tell me isn't real, but mathematically it ends up happening. So we're going to treat it like it's real, even if it's debatable, because mathematically it shows up, which is relevant for why you get these different values in your instruments. So this is just a quick review. I'm not going to go through all the math, but I believe we distribute the slides so you can have all this fun math to determine these if you like. But again, we have that pure zero phase angle situation where voltage and current are aligned, and we get power that's purely positive but oscillatory. We have that 90-degree phase angle where perfectly misaligned, so we have that oscillating power, which averages out to zero. And then we have the realistic situation of sub-phase angle in between, where we have an element of real and an element of oscillatory or reactive power. So I won't belabor this. I'm definitely not going through the math. We have a brilliant guy named Andrew Halfpenny who can go through all of this if you like. It's phenomenal to listen to.